Photoelectric Effect. The second clue to the quantum nature of a radiation came from the study of the photoelectric effect. As we will see, the photoelectric effect, like blackbody radiation, cannot be explained by classical physics. By the way, if you like this video, don't forget to like and subscribe to this channel and activate the bell. It's very important for the continuity of this channel. When a metal surface is illuminated with light, electrons cannot be emitted from the surface. To escape from the surface, the electrons must absorb enough energy from the incident light to overcome the attraction of positive ions in the material. This effect is called the photoelectric effect, and it was discovered by Hertz in 1987 in the process of his research into electromagnetic radiation. The emitted electrons are called photoelectrons. A simple experimental arrangement for observing the photoelectric effect is illustrated in figure below. An evacuated glass tube known as a photocell contains a metal plate, the emitter, connected to the negative terminal of a variable power supply. Another metal plate, the collector, is maintained at a positive potential by the power supply. When the tube is kept in the dark, the emitter reads 0, indicating that there is no current in the circuit. But when light of sufficiently high frequency illuminates the emitter plate, electrons moving from emitter plate to collector plate create a current in the circuit, registered at the emitter. We now use the experimental arrangement to study the variation of a photocurrent with the intensity of a radiation. The graph below shows us the photoelectric current versus the potential difference between the plates for two light intensities. The current increases as the incident light intensity increases. This implies that the number of photoelectrons emitted per second is directly proportional to the intensity of incident radiation. At sufficiently large voltage, all the emitted electrons reach the collector plate and current reaches its maximum value. Classical physics works pretty well so far. The higher the light intensity, the more energy reaches the emitting plate, and the more photoelectrons are removed from the plate. We now use the experimental arrangement to study the effect of potential on photoelectric current. The illuminated plate emits photoelectrons with various kinetic energies. But by reversing the field and adjusting its strength, we can prevent the less energetic electrons from reaching the collector plate. In fact, we can determine the maximum kinetic energy of the emitted electrons by making the potential difference just negative enough so that the current stops. This can be done by using a variable voltage source and reversing the terminals, so that the emitted plate is positive and the collector plate is negative. As an electron moves from right to left, the potential decreases and negative work is done on the electron. This negative work is given by charge times potential. The electrons are repelled and only the most energetic electrons are able to reach the collector. The initial kinetic energy, the most energetic electrons, is given by the photocurrent is found to decrease rapidly until it drops to 0 at a certain sharply defined critical value of the negative potential V on the collector plate. This critical value of the negative potential is called the stopping potential, or stopping voltage, and from its measurement, the maximum kinetic energy of the photoelectron can be determined by using the work energy theorem. The experimental result is illustrated by the graph. The graph shows us that for a given frequency of radiation, the greater the intensity of radiation, the more electrons are being emitted per second, proportional to the intensity of incident radiation. But the stopping potential remains the same regardless of the intensity of the incident radiation. Thus, for a given frequency of radiation, the stopping potential is independent of its intensity. In other words, the maximum kinetic energy of photoelectrons depends on the light source and the emitter plate material, but is independent of intensity of incident radiation. This result cannot be explained with classical physics because, according to classical physics, increasing the intensity of the light source increases the electric field of the wave, which also increases the force on the electron and its kinetic energy when it eventually leaves the surface. Hence, for the same frequency of radiation, the greater the intensity of the radiation, the greater the stopping voltage should be, and the graph according to classical physics is given below. Therefore, the classical physics is disagreement with the experimental result. Three other features of the photoelectric effect can be explained with classical physics. The photoelectric effect does not occur at all if the frequency of the light source is below some cutoff frequency. This value is characteristic of the kind of metal surface used in the experiment. This fact is inconsistent with the wave theory, which predicts that the photoelectric effect should occur at any frequency, provided the light intensity is sufficiently high. Since electrons are held in the metal by attractive forces, some amount of energy is needed to do the work to overcome the attractive forces that act on the electron within the metal. This energy is called the work function. The wave theory predicts a time delay before electron emission so that an electron can absorb enough energy to exceed the work function. But electrons are emitted from the surface almost instantaneously, even at low light intensities, and no measurable time delay is measured. A successful explanation of the photoelectric effect was given by Einstein in 1905. Einstein assumed that the energy quantization used by Planck in solving the blackbody radiation problem was, in fact, a universal characteristic of light. In this picture, the energy of electromagnetic radiation is not continuously distributed over the wavefront, but instead is concentrated in localized bundles or quanta, also known as photons. The energy of a photon associated with an electromagnetic wave of frequency f is given as follows. In photoelectric effect, the entire energy of the photon is absorbed instantaneously to a single photoelectron. If the photon energy exceeds the work function, the excess energy appears as the kinetic energy of the electron, and the spin potential should be given as follows. With the photon theory of light, we can explain the previously mentioned features of the photoelectric effect that cannot be understood using concepts of classical physics. Photoelectrons are created by absorption of a single photon, so the energy of that photon must be greater than or equal to the work function, else no photoelectrons will be produced. This explains the cutoff frequency. Electrons are emitted almost instantaneously regardless of intensity, because the light energy is concentrated in packets rather than spread out in waves, so that no time delay is necessary. An increase in intensity of the light beam means more photons are incident, so more electrons will be ejected. But since the energy of each photon is not changed, the maximum kinetic energy of electrons is not changed by an increase in intensity, and the stopping potential increases with increasing frequency and is independent of intensity. Let's see how it works. Pay attention in the example. To calculate the work function, we take the expression for the maximum kinetic energy and set it to 0. To find item B, we first calculate the energy of each photon for the given wavelength. We now use the photoelectric effect equation. Finally, we find the maximum speed